The Chatelier's principle is a simple qualitative tool to predict the shift of a chemical equilibrium. It says if a system at equilibrium is disturbed by a change of pressure, temperature, or a component concentration, the system will shift its equilibrium position to minimize the effect of the disturbance. Now let me use this picture to explain how to use this principle to predict the shift of a chemical equilibrium. Suppose there is a chemical reaction which is already at the equilibrium. Let's call this a regional equilibrium position. If you want to increase the concentration of a component by adding that component to the chemical reaction, that component can be a reactant, it can also be a product. After you add that component to the chemical reaction, this is the new concentration of that component. The Chatelier's principle says the chemical reaction will try to minimize the change of that component, which means it will try to decrease the concentration of that component because the disturbance will increase the concentration. The reaction will try to minimize the increase of the concentration. Well, I want to emphasize, compared to the original equilibrium, the component concentration at new equilibrium, it is still higher than the concentration of that component in the original equilibrium mixture. This is because we added that component to the system. Even the reaction tried to minimize the change, we still have more that component compared to the original equilibrium mixture. Now let me use an example to explain how to apply this principle. After an equilibrium is established, ammonia is added to the system. Please answer the following questions. A. What direction will the reaction go to? B. At new equilibrium, are we going to have more or less hydrogen than the original equilibrium mixture? C. At new equilibrium, are we going to have more or less ammonia than the original equilibrium mixture? Since we added ammonia to the system, the concentration of ammonia should increase. The principle says the reaction will try to minimize the increase of ammonia. Therefore, the reaction should go to the left. If the reaction goes to the left, the concentration of hydrogen will increase. Therefore, we should have more hydrogen in the new equilibrium mixture than the original equilibrium mixture. When the reaction goes to the left, the ammonia concentration should decrease. However, since we added ammonia at the beginning, we should have more ammonia in the new equilibrium mixture. In other words, although this principle predicts the chemical reaction will try to minimize the change, it doesn't cancel the change. Even the reaction goes to the left because we added ammonia at the beginning. We should have more ammonia in the new equilibrium mixture, as this picture shows. This is an old equilibrium mixture. This shows the concentration of ammonia. When we add ammonia to the system, the reaction will try to go to the left. But when the reaction goes to the left, it doesn't cancel the increase of the concentration compared to the old equilibrium mixture. Therefore, when we compare the new equilibrium concentration of ammonia to the original equilibrium mixture, we still have more ammonia in the new equilibrium mixture. Now let's look at another example. Predict the effect of decreasing the total pressure by increasing the volume at constant temperature on the following reactions at equilibrium. When we try to decrease the total pressure, the Chatelier's principle predicts the chemical reaction will try to increase the total pressure. If the chemical reaction wants to increase the pressure, it has to shift to the direction that has more moles of gases, because more moles of gases means higher pressure. Which means for the first reaction, since we have 3 plus 1 equal to 4 moles of gases on the left, and we have 2 moles of gases on the right, If the chemical reaction wants to increase the total pressure, the reaction should go to the left. For the second reaction, if the reaction wants to increase the total pressure, it has to shift to the direction that has more moles of gases, which should be to the right, because the right has 2 moles of gases and the left has only 1 mole of gas. For the third reaction, the left side has 1 plus 1 equal to 2 moles of gases. On the right side, there are also 2 moles of gases. Therefore, decreasing the total pressure by increasing the volume will have no effect. Now let's look at the third example. Predict the effect of increasing the total pressure by adding inert gases, such as helium, at constant temperature on the following reactions at equilibrium. Although, when we add inert gases to the equilibrium mixture, the total pressure can increase, but the partial pressures of all gases will not change. Therefore, when we add inert gases to any chemical reaction, there will be no effect to the equilibrium. Now let's look at example number 4. Predict the effect of increasing the temperature on the following reactions at equilibrium. For the first reaction, delta H is positive. That means it is an endothermic reaction. If the reaction goes to the right, it will take in heat. That means it will decrease the temperature. From Le Chatelier's principle, if we want to increase the temperature, the chemical reaction will try to decrease the temperature, which means for an endothermic reaction, the reaction goes to the right. For the second reaction, delta H is negative. That means it is an exothermic reaction. If the reaction goes to the left, it will take in heat. That means decrease the temperature of the chemical reaction. From Le Chatelier's principle, if we want to increase the temperature of the chemical reaction, the reaction should try to decrease the temperature, which means for an exothermic reaction, the reaction should go to the left.